Hi everyone, good morning. I'm Kikuchi Yutaka from Kochi University of Technology in Japan. I'm talking about our trial to apply Elixir for small hydropower plant. I gave a talk about this plan at Elixir Conf US 2020. I'm delighted to report here one of the results of that time. So let me introduce myself first. I'm a researcher at Kochi University of Technology. Unlike other professors, I'm in a unique position to seek partnership with local businesses. In addition to this, I'm a member of a renewable energy startup named CloudGrid. Also, I'm a member of Elixir-related communities, Nerves JP and Kochi EX. Today, I will speak in this order. First, our background, introduction to small hydropower and our history. Second, I will show you the issues we faced before. Third, I will tell you our past trials. Fourth, I will show you our current works, and I will conclude it. Before starting the presentation, I want to explain some technical words you might not be familiar with. FA means factory automation. When I use the word FA, that means systems for individual use. Scada stands for Supervisory Control and Data Acquisition. We often say Scada is a remote OAM, operation and management system in the FA field. PLC stands for Programmable Logic Controller. That is a kind of computer system, simulated electromechanical equipment, popular and traditional conventional computer used in FA. IoT means industrial IoT, mainly used in more severe environment as FA. There is no concrete definition of SHP or small hydropower, but in main cases, small means that the maximum power is under 1,000 kilowatts. What we want to do, in a nutshell, is to make a happy FA environment with Elixir. We want to make evidence that we can use Elixir in the FA field. I will show you that we prove it to apply Elixir to our SHP in this talk. The area of small hydropower plants is just a small portion of the whole FA field, but it turns out how we should do it. I'm introducing an overview of small hydropower plants. The principle is very simple. It uses very Newtonian mechanics, neither Einstein's nor quantum physics. So it gets water from some higher altitude place of a river with an intake facility and bringing water flow to a head tank to get higher water pressure with a penstock. And so that you can get electrical power in the powerhouse. The power you get depends on flow and head. Head means the altitude difference. In the powerhouse, there is some equipment. The turbine converts water pressure into rotational torque. The generator converts rotation torque into electrical power. That is, some power control system is in the switchboard. The transformer matches the generator output to the grid voltage. And all the facilities are regulated with a control system. There are three main functions of the control system. The first is regulation to get maximum power. The water flow changes, so the system should get maximum efficiency according to the water flow. Second, is an important function to protect against troubles. The powerhouse must securely shut down when it detects some abnormal conditions. Unless this function, the equipment would be damaged, the operators would be injured, and have a trouble effect into the power grid. The third one is today's main topic. Is Scada to monitor, to operate, and to record logs internally and remotely. The facilities would be located in the intake house and the powerhouse and the cloud. The regulation system and the protection system could be realized with conventional PLCs because they are on the same line. In the other way, Scada, on the other hand, needs to be made on a widely distributed network, for example, on the internet. Conventional PLCs are not good at making this function. This slide shows our first experience in building a small hydropower plant in 2016. The photo in the right-hand side is a full view of the power plant. We take water from the river at the intake, as shown in the left-hand side. The center photo is an inside view of the powerhouse. The head or the altitude difference between the intake and the powerhouse is about 100 meters. A Francis turbine gets water at 200 liters per second, and an induction generator produces 145 kilowatts at maximum. It has been producing 800,000 kilowatt-hour a year, which corresponds to about 200 houses, typical houses in Japan. In this experience, we made a Scada of the plant with conventional PLCs to control the plant's equipment, and 3 Raspberry Pis to collect log data and for remote operation. We met some issues in this case. One is there were 2 subsystems in different ways. We needed to use 2 different languages, 2 different natural languages to communicate with both PLC engineers and web engineers of Raspberry Pi, because their technical standpoints are completely different. The other issue is reliability of Raspberry Pis that are not for industrial use originally. So 1 out of 3 Raspberry Pis has broken every year. According to this experience, we tried to make Scada the other way. I'm showing you 2 more references. This smaller one started in early 2018. It gets water from a sand trap dam. Sand trap dam, you can see the right-hand side photo. And that already exists. It produces about 50 kilowatt with a Kaplan turbine. These images are the smallest hydropower plant we have made before. There is a skiing ground at the upper right of the right-hand side photo. Over there, ski ground. So the owner of the ski ground uses spring water from the ground to make artificial snow at the beginning and the end of the ski season. He wanted to use spring water for power generation when he does not need to make artificial snow. This Pelton turbine produces about 20 kilowatts. In those two plants, we made new Scada system at first. We made a new hardware box that runs Linux instead of using both PLC or nor Raspberry Pi. We made a regulation system, a protection system, and a Scada in Python language. The box sends the log data to AWS and receives operation orders from the operator via the internet. Here we have some issues from those experiences. About hardware, we need robust ones that protect from high and low temperature and humidity, and sortless write operations to SD card. We selected Python language at that time without deep consideration. I do not know about the current Python, but at that time, Python had no concept of concurrency. Therefore, the Scada system runs on just one thread. Sometimes the system responds very dully. For example, due to slower internet communication or long timing of AD conversion. Talking about small power hydro plants, we do not need hard real-time systems because there is no critical control. However, we cannot overlook this kind of dullness. The other problem, Python is a scripting language processed by its interpreter, which may cause runtime crash more than compiler language. So according to the discussion, we decided to the Elixir language. There are concepts of concurrency and let-it crash concept from Alan. Elixir has friendly syntax, macros, and protocols. And I know this is off subject, but I want to point out that the hot reload function of Alan would be necessary for FA applications because conventional PLCs can do it. The second decision is to make specialized hardware for our use. It should be much more robust against temperature and humidity stress. Also, it should be much more friendly for the selected language, in this case, Elixir. To make special machines that run Elixir, we adapted to use Nervous. As you know, Nervous is the platform of IoT in Elixir. It prepends small board computers as Elixir machine, because it has underlying systems, for example, operating systems and I/O details. It also reduces the cost of handling IoT systems because it works almost on the IP protocol. Therefore, it is possible to apply engineers, even those who do not know IoT very well. For example, web engineers, we can hire and they can work on the industrial IoT products. Here comes our Elixir machines, names HB. These boards are based on BeagleBone Green, which is a BeagleBone clone by Seed Studio. So we need not make much effort to design circuit boards and build a Nervous kernel, because the circuit schematic and kernel codes are in open source. Different from conventional PLCs, our modules have their own CPU. Therefore, all the modules run individually and may be connected with the function of node connect in the same local area network. We use OSD 3358 CCIP by Octave Systems, which contains almost everything to make small board computers. Cortex A8, eMMC, popular I/O interfaces, and many power line capacitors. we made three types of modules. One provides separated digital I/O interfaces, and one provides analog I/Os, and the other provides a combination of the various kinds of I/O interfaces, including RS-485. All the modules have PoE, or Ethernet interface with a power supply line. They all have capacitance bigger enough to shut down the OS on power cut. The left-hand side is inside of the combo module. Upper right is the digital I/O module, and the lower is the inside of analog I/O modules. And we checked with stress tests that include higher temperatures, lower temperature, and higher humidity according to the IEC standard, IEC 61131-2. It's a standard of the PLC machine, but we tested according to this standard. Also, we checked our modules with vibration and physical shock according to the standard. It was proven that our modules are robust enough as conventional PLCs. After that, we got an order to make a small hydropower plant in Nozawa Onsen. That is a village located in Nagano Prefecture in Japan. It is a famous place for skiing and hot spring. Sorry, not so smooth, but here comes intake. There is a canal used for agriculture canal. So here is powerhouse. So the mayor of the village declared that the Nozawa Onsen village would be a village that promotes renewable energy. So they wanted to use an existing agricultural channel as also for small hydropower. In this SHP, we prepared two nervous machines. They are located in the different places, but on the same network connected with optical fibers. One is at the intake, which measures the water level of the head tank for regulation, and also to control an out screen. The out screen is to remove garbage and leaves from the water. The other one is in the powerhouse to communicate with with the PLC that controls the facilities. PLC controls the facilities via an individual industrial protocol named Modbus TCP. Also, it composes a Scada with a web server and GCP components via HTTP and MQTT. These two drawings show the structure of the software. The circles mean gen server processes. I do not explain the diagram in detail here, but the design and coding had been written by two engineers who were initially working on web systems. The delivery time is much limited, but they finished the work on time, which shows Elixir is suitable for industrial IoT. This is an opening ceremony of the power plant in the afternoon of the 30th March this year. Watch the view from the sky around the small hydropower plant in the village. Sorry for in Japanese. It's the intake. Here is junior high school. And here is canal for agriculture. over there, ski place, and there are many public baths from natural resources. You can enjoy naked communication with Japanese in the public bath. So anyway, here is their powerhouse, and penstock is under the ground. You cannot see the penstock directly. This is the opening ceremony. He is the mayor, and he hit the button, and the powerhouse starts to generate the power. Okay, that's a very ceremony. So let's go to the next. So I will try demonstration. So here. Come on, come on. Alright. Ah. Ooh. Wrong condition. Here is a canal, and there is an intake house where water comes from here to there. Most of water is used for powerhouse. And now Japan is maybe 2 or 3 o'clock, just after midnight. So it is, this video is in intake house. This is auto screening system, so to remove garbage and leaves. So this is remote control buttons. This starts the generation. This stops the generation. And in case of emergency, we can use it. And today, I don't try to use it. So just one. This starts the auto. I forgot the name. Auto screen. And auto screen runs periodically, and we can move them manually. So let's get started. This is confirmation window. I must input same as I saw, and OK. And this is a message in Japanese, so means the auto screen was started. So really started. Okay? Yes. Thank you so much. This is trans-Pacific operation, so yes. So far, I have presented our work to date. Then I will talk about our concurrent work in the our current work in the rest of this session. How much time is left? 10 minutes? Around? Okay. So, first, we use the Elixir in some parts of the SHP. Next, we are producing a small hydropower plant controlled with only Elixir without any conventional PLCs. Second, mobile communications technology is coming into the FA field. So we should mind how to construct systems with those technologies. Now we are working on a small SHP. SHP means small, but more small SHP construction in the steep mountains in Tsurugi town. Here is 2.5 hours to go from our university, so it's a very steep there is intake, and here comes powerhouse. So the owner is an individual, and the power is less than 50 kilowatts. So therefore, he cannot earn much money. Then it is a kind of garage power plant. So we have been making a control system for this plant in Elixir with our 2 nerves machines. In this case, the regulation, the protection, and the Scada will be written in Elixir. The small hydro plant will be finished in this month. Unfortunately, I would talk about this plant, this session, but I can't. So I found it very interesting that 2 styles of development are possible. Last time, we worked with web background engineers in design and coding. This time, we are working with an engineer with a production machinery engineering background to design and coding. So the letter uses many smaller gen server processes communicating with PubSub. So it will be finished soon. So I will report about what will happen in such a difference. It's very interesting. So former SHP, they make processes as functional modules. Now he wants to make gen server processes per if-then rules and communication with PubSub protocol. So it's very, very interesting. So, and the last topic is how to construct FA system with mobile network technologies. Today, typical commercial distributed systems are combined with devices and clouds. So they are connected via the internet. The internet does not have computing resources itself. Now, here comes a big wave that the current mobile network technology called 5G or 5th generation allows computing resources in the network. We call it MEC, or multi-access edge computing. Those are computing resources spread in the network talking in IP. And surprisingly, we can attach our own 5G base station to the network, even if you are not a mobile carrier. It is a kind of civilization of mobile networks. The photo on the right-hand side are of the local 5G core and its antenna for our research in our university. With the advent of Mac, the situation for distributed computing became very complex because there would be a variety of computation resources whose power and price would be much different. Also, the network quality is varied: latency, jitter, packet loss rate, and so on. How should we combine those resources into one system? We have been working on research projects that enable systems development much easier on such networks, including 5G MEC. It consists of some technologies. Some of them are presented in Dr. Takase here, presented the presentation yesterday. So, for example, PubSub middleware over the internet and edge device with heterogeneous SOC, right? So we are making a computation platform with edge devices, clouds, and Mac in Elixir. The platform will enable the developer can construct a distributed system over networks without being aware of details of underlying structures. I hope we will report on this research project in the future. So I conclude this presentation, which shows the practical industrial proof of FA in Elixir, which with nerves. The engineers developed the industrial IoT system with pleasant development experience, even though their origin was not from IoT. We are still making the other proofs of FA systems. They will demonstrate we can use Elixir in FA field as well. We have a plan to construct a new platform for the development of distributed system over 5G mobile networks. So acknowledgements, part of our commercial product development and research project has been supported by NICT and the Kochi Prefectural Government. I want to say my special thanks to the member of Kochi EX, Kazuma, Mitsu, and Miyasu. Thank you for the open source hardware and its kernel code by BeagleBone team and Seed Studio company. Thank you to Beam and Alan and Nervous Project, Elixir and the Nervous Project team and communities. And finally, I want to thank to my family. My wife Michiko made some of the drawings and icons in these slides. Thank you for the great graphics for my presentation. And to the audience here and out of here, thank you very much for your attention. Thank you.
All right, so thanks, Yutaka. We have two questions from the virtual audience, so let me just read out for you. Could you describe the hardware cost of your system compared to a traditional PLC? So what's more expensive, like a PLC or your system? Can you compare it?
Can I see the
Yeah, absolutely, absolutely. Go ahead.
Could you describe the hardware cost of your system compared to the conventional PLC? Good question. I should explain the cost of traditional conventional PLC and our system. How do I think? Yeah. Our machines are so compatible to the traditional PLCs, but we made much more boxes. The cost would be down, and our machines will be competitive to the other system. Other PLCs. But cost comparison is not so good, so not so good idea. So because there is much different development process, PLC and our system with Elixir. So maybe in the future, including the software development cost, our scheme is much better than traditional PLCs, I think. Is this the answer of the question?
Yeah. I think it'll be a matter of time to see if it's cheaper than traditional PLCs. It's too young of a project right now. And the other question we have here is, what do you gain by eliminating all the PLCs and using just nerves clusters? Are there any challenges in terms of protection? Yeah, go ahead.
Response time. Yeah. Actually, conventional PLC has hard real-time property. So the Elixir on the Linux should not be hard real-time. So that's a problem. In this case, small hydropower plant need not to use hard real-time system. But we cannot, maybe we cannot use the control system of the generation, control system of power plant with boiler or some kind of nuclear. We should not use this system at the power plant, I think.
I think, as you say, maybe it's more of a case use. You'll try to see when it's not dangerous to use these type of things because it's not super real time. Yeah.
Right.
All right. Yep. Question here.
はい、とても面白かった。ありがとうございます。
ありがとうございます。
Can we buy one of your XBs? Is that something we can buy from you?
I'm sorry?
Can we buy one of the XBs from you, one of your devices? Buy it. Yeah, I want to buy some.
My board?
Yeah, I want to buy some.
I will sell you?
Yeah.
Yeah, he has some there.
Yeah. I want to, but according to the lack of semiconductors in the world, we cannot make other boxes. I try to next boxes, but I can't now. So if I can provide you, so I will send you your invoice directory. So, okay, maybe yes.
Thanks. So anyone else has a question? Yep.
Thank you. That was a good talk. As we just saw you log into a hydropower plant in Japan and play with settings, what kind of security is there to prevent somebody else from doing the same?
なんだって。
今アメリカから日本のプラントを動作されましたんですけれども、もし第三者の方が悪いのつもりでログインして、そういうリスクを控えるために何すればいいのか。
Yeah. According to the security, there is no special scheme. There basically password and ID and one-time password and HTTPS, using HTTPS and using MQTTS and not special. So in this case, this system is so-so. Okay. Actually, I'm wondering to demonstrate about this demonstration because there must be, you can see the URL on the top of the screen, and there is a vulnerability to our system. So
you just told everybody that. Thank you.
All right. Okay, so seems like I'm the only one that doesn't speak Japanese today. Anyone else? I think we have time for one other question. Righty then. We'll have a 5-minute break until we set up the next talk. Thanks, everyone.
Thank you very much.